So, what happens when a wave meets another wave? Is it love at first bump? Well, we're going to get what's called an interference pattern. When two wave or more waves overlap and combine together, what's going to happen is we're going to have constructive and destructive interference. So this is how how wave properties differ from what from particles. So if you want to know what a difference is between a particle and a wave is, well, this is how you know. Okay. So let's say you have two troughs coming at you, and the trough is a -1 plus a -1. What's a -1 plus a -1, by the way? Oh, it's a -2. So what happens when they meet, they add together. The math is actually really easy on this amplitude stuff. You just this plus this, and they meet together and they make this. So you get a -2 here. And then what happens is the red keeps on moving this way and the blue keeps on moving this way as if they had never even met. So this is the difference between a wave and a particle. Particles, when they meet, oh my goodness, that could be elastic, could be an inelastic collision. Things are bouncing back the other direction and everything and changing speeds. Well, that doesn't happen here. So whatever this is, a -1 plus a -1, you get a -2 here, but then the red keeps on going -1 this way, the blue keeps on going that way. What if you have a positive one and a positive one? Well, they get a +2. So this is called constructive interference because it's getting larger, either larger in the negative or larger in the positive, but the math is actually pretty easy. Okay, what happens if you have what's a +1 plus a -1? Well, when they meet, that's 0. At the instant they meet, that's a 0. Then a moment later, the red keeps on going this way to +1, the blue keeps on going this way to -1. These are particles that wouldn't happen. So what happens is they constructively and destructively interfere, but then they just keep on meandering on their own merry way. So at this particular point, they destroy each other at this point. But not for good. Only at this instant is it 0. In a moment, this is moving this way and that's moving that way, and it gets a lot smaller and goes back to the way they were moving. What happens if you have a +1 and a -2? Well, +1 plus a -2 is a -1. So as soon as they meet, it's going to be a -1 right there. But the difference between a particle and a wave is it's going to keep on moving right along its merry way, and so will the negative over here. That's called destructive interference. Okay, so they subtract. So constructive is where they add together. Destructive is when they subtract from each other. And when that happens is you can get what's called a standing wave, which I'm going to show you in a moment. So right now it may not make a lot of a sense at this moment, but what happens is to make a standing wave, we need a boundary and something maybe to pluck a string, like this could be a guitar or something else. And so let's say if the first pluck, you pull the string down, it goes down, and that travels this way. Hits this, inverts, comes back up, and comes back the other way. Well, if you keep plucking this thing, what's going to happen is as it hits this side, it's going to invert, come back this way. You could actually get what's called a standing wave, where the waves always hit. So the wave coming this way, as it reflects back, now the wave coming backwards meets the wave coming forwards, and here they destroy each other for the moment. Here they add together, and here they destroy each other. So the nodes are positioned where you have destructive interference. The antinodes are constructive interference. So it's either up or down. So this would be an example where plus meets plus gets a super plus, or a minus can hit a minus, which is a super minus. It can be either or, and they're all going to flip back and forth, as you'll see in just a moment. So our terms are nodes are points of destructive interference. Antinodes are constructive interference. Okay, so the node is where there's no displacement of the medium of a standing wave. Antinode is where there's a maximum displacement of that medium of the standing wave. So let's go look at another simulation. Hopefully it doesn't take a half an hour to load up. Oh my goodness. It could be slow here, people. There's my spinning wheel. And I might pause for a second here just to save some. Nope, here we go. Here we go. Now we're moving. Okay. So what I'm going to do is I'm going to take the dampening off of this thing so the wave doesn't really die off. So have you noticed when you shake this, you get a wave going through this? No dampening, it reflects back this way. The idea is to get the timing on this thing. To get the timing just right, when I add another wave, so you notice when it comes on, it hits. As soon as it hits, I'm going to try to give a positive push. As soon as it hits, give it an extra oomph there. Here and oomph. I missed a little bit. Let me try that again. Oomph. If every time it comes around I give another little oomph right at the right spot, I've got to do the up and down. Now it's all crazy. So I'm going to put some dampening on this and get rid of my craziness over here. Lots of dampening. Oh, settles down. So dampening is kind of like a friction where the energy of this dies out. Okay? On a guitar, there's natural dampening just because you can't get something for nothing. As that string vibrates, you're vibrating the wood, and that energy permeates out into the air, and that energy is taken off the string into the wood vibrating, goes into the air, and so on, so the sound dies off over time. That's a dampening. Okay, so here's what I've already done. I already found out that on high tension, the speed of a wave going this way. And the way I found that is by just doing a pulse. And I put my ruler on there and I put my timer on there, and what I did is I sent a pulse out through there, as you should have done earlier. And to be for precision, I timed 10 of these, down and backs, down and backs. Every trip down is a 7.5 centimeters. Every trip back is 7.5. That's 15 centimeters total. So I took the time for 10 down and backs, which is 150 centimeters total distance, and the time was like 23.8 seconds. So I know the speed of my wave is 6.3 meters per second. And unless I change the tension, there's nothing I can do. Okay? There's nothing I can do to change the speed of this wave. It's always going to travel 6.3 unless I change the medium. By changing the mass of this string, by changing the tension on this string, those are just a couple examples of how I could change the medium, but I don't have any way to change the mass. I only have a way to change the tension. We'll get to that in a moment. So here's my point. Now that I found that the speed of this wave is 6.3, I can go back and find a wavelength that's going to reflect nicely back and forth to make a standing wave. So if I want to make a wave where I get an up and a down on this, so I have two antinodes, so a full wavelength, that means my wavelength would be 7.5 centimeters. So I took my velocity from my wave equation, my 6.3, divided it by the wavelength, 7.5 centimeters. That's 6.3 centimeters per second, by the way, and I got a 0.84 hertz. So what that means is if I go to oscillate now, and so I got some craziness going there. If I go to 0.84 hertz, I should see one wave on there. Oops. And I'm going to do some dampening. And we'll start that again. Okay. So here's what you should, whoa, look at the thing going nuts. Oh my goodness. And the reason it's going nuts right now is because that when this sends a wave, every time it goes up and down, it sends a wave. And the wave hits this side over here, reflects back inverse, come back this way, and it meets the next wave. Well, what's happening right now is I'm getting all my peaks to match right here. I'm getting a positive hit a positive and a negative to hit a negatives right there. And if I slow down the motion a little bit like this, what happens is at the very highest moment here, I'm getting my two peaks to match. Here, I'm getting the two negative peaks to match at that point as it travels. But what happens right here in the middle, halfway between 7.5, which is at 3.8? So at 3.8 here, we have basically, or 3 point, yeah, right in this area right here, 7.5, whatever it is, right here, we have destructive interference. This is where the peak always meets the trough. So as the peak is coming this way, it's always meeting the trough here, and whatever size it is, they cancel themselves out. This is called a node. This is a node, and even though this is moving, it's minimal displacement. We still call that a node. So the antinodes are maximum displacement over here. Now the reason, once again, that your guitar or violin string doesn't get quite as crazy as that, you got a little bit of dampening going on. So with a little bit of dampening, it doesn't get quite as crazy, and some of that energy goes into the wood. Some instruments goes more that, like a banjo, it doesn't sustain very long because a lot of the energy goes very quickly into that little drum head that the bridge is on. And so it doesn't sustain very long. They need another pluck to keep the music going. But there you go. So there's a little bit of dampening, but you can see there's the antinode, there's the node, there's the antinode. And this wavelength right here is 7.5. Turns out this string can naturally vibrate at a lower frequency than this. And the frequency that this can naturally vibrate at is actually half of this, or 42. So let me go down to 42, which is half the frequency. Let me go a little faster down to 42. There we are at 42. Let's do high dampening to get rid of this, or otherwise I just have to start over. And no dampening. So here we go. Now we're going slow. Wave coming in. It inverts coming out. As it added one coming out, now it's reflecting back going down, and it's adding a negative to that same point. Notice how big this is getting. Whoo! This is getting huge, folks. So this right here is half a wave. You have one full antinode. Okay, you have one full of the hump here, either way you have peak meets peak or trough meets trough, and they only destructively add together at each end. So this is called the fundamental frequency, or the lowest frequency at which a string instruments can vibrate at, which is a half of a wave. Okay, so the next so I can't go any lower. If I go lower, I will not get a standing wave. Nothing will meet at the right points to make this thing go like crazy here. This is the lowest frequency, 0.42. If I go one octave up, that's the second harmonic, which we actually already saw was a 0.84. And we restart at the 0.84. Let's go to normal speed to make this thing happen faster. So that's called the second harmonic, which is the second highest frequency, which is one octave higher than the fundamental. So it's twice the frequency. Remember, we're not changing the speed. We're changing the wavelength, and so the frequency is changing by the same amount. Since we have half the wavelength now that we just had before, we actually have twice the frequency, which is this is called the second harmonic, 0.84. We can go to the third harmonic, which is 3.42s, which is what, 1.26? So go to 1.26, dink, dink. Let me restart this thing. Here we go. So you notice now this is the third harmonic, so we actually have 3 humps if I slow down the motion for you. So 3 humps mean 3 antinodes. Now we have 4 nodes, node, node, node. Those are points of minimal displacement where you have destructive interference. The peaks, you have constructive interference. So this is your third harmonic. And if I wanted to go, let's do one more fourth harmonic. That means we're doing 4.42s, which is what, 2.08. Oops, I missed. And so we start this sucker. So if this is 4 times the fundamental, what do you expect to see? 4 humps. Or 2 separate ways. Oops, what am I at here? Oh, I skipped maybe 4. I think I went right up to 5. I did. I skipped the number 4 and I went up to 5 times 0.42. This is the 5th harmonic, where I have actually 2.5 waves. So each wave is like 3 centimeters long. That's 3 centimeters. This is 3 centimeters. Then for my last centimeter and a half, I got the last half wave. So this is the 5th harmonic, or 5 times higher in frequency. Okay? All right, let's go back to our PowerPoint here. Oops, not that one. This one. All righty. So here's what we have. So we have lots of different harmonics that could happen onto this thing. And this is called the fundamental. This is called the fundamental, the lowest that a string can vibrate at. This is the second harmonic. You have 2 humps. Third harmonic, so this is twice the frequency of that. This is 3 times the frequency of that. This is 4 times the frequency of that. This is 5 times the frequency of that, but it's 1/5 the wavelength. Because remember, the speed's not changing. So we can have all kinds of these harmonics on the string. And one way to find them is you pluck a string and you put a finger right here. Put a finger right here, you dampen out that one, and you only have that one sounding out. Quick example of that, if I pluck this big string over here and I touch it right in the middle, you hear that? Get rid of the fundamental, you're hearing the second harmonic. If I want the third harmonic, I go to 1/3 the length,